All right, hello everyone. Part of this talk will also be done by Josh. I will only be talking for half the time. So yeah, I'm pretty sure everyone knows about axions here, but not everyone necessarily knows about neutron stars. So I thought I should probably start with a little very brief summary about what neutron stars actually are, what they're made of, and why they're so important for axion physics. So this is a very colorful representation of a neutron star. And generally, a neutron star consists of a couple different layers. You have the core, the inner core, and the outer core. You have, and this pointer doesn't work anymore, so I'm just going to ignore that. You have an inner and an outer core. The stick. Oh, the stick. So we have the inner and the outer core, and we have a crust. The outer crust, also sometimes referred to as an envelope, and we have a small atmosphere. Now, a neutron star is somewhere between 1 and 2 solar masses heavy typically, and it's relatively small with the radius of like somewhere around 12 to 13 kilometers. So those numbers are all very rough. Of course, there's some variation to it. Of this, the inner and the outer core make up most of it, with the outer crust being just 1 to 2 kilometers thick. And then the atmosphere is, depending on the neutron star and depending on who you ask, just a couple micrometers or a couple centimeters thick. The terms of, as you can imagine, if you have 1 to 2 solar masses crammed into an object of 13 kilometers of radius, the densities are incredibly large in the middle. So in the center, the densities can reach around like 10 to the 15 grams per centimeter cubed, with this around roughly twice the nuclear density. The outer core and the inner core is distinguished by where it actually hits the nuclear density. The outer part is quite a bit less dense, but it's still about a ton per centimeter cubed. Now, the temperatures that I give here, so the inner core is about a keV, with the outer surface just about 100 eV. Those temperatures are for relatively old neutron stars that have already cooled down. So younger neutron stars can be significantly heavier than what is shown here. And there's typically ways, given that we can't actually access the core, and actually measure the temperature. There's a relation that one can work out in order to infer what the core temperature is from the surface temperature, though there's quite a little bit of uncertainty on that relation, of course, depending on what you assume, what like the outer crust in particular is made of. Now, in terms of what the neutron star is actually made of, well, it's a neutron star, so you would assume most of it is neutrons, which is actually true. A lot of them is neutrons, but you also have other nuclei. You have protons, you also have electrons and muons. And the ratio between neutrons to proton is roughly 2 to 1 to 3 to 1, somewhere around that range. So there is actually a significant amount of protons as well as leptons in the central core as well. Now, the central part, given that it has such a high density, is typically a Fermi liquid, so Pauli blocking applies down there. And there's also the theoretical assumption that the central core could actually be also a superfluid, could be in a superfluid state, which would mean that you can form Cooper pairs of neutrons and of protons in the central core. But whether the core actually is superfluid is something we don't necessarily know. But in theory, it could be. Now, these electrons and muons in the central core mostly coming from other processes where you have, for example, the modified Orca process, where you convert a neutron to a proton and you can produce a lepton together with a neutrino. The outer parts, the crust, that's where like the elements start to become a little bit heavier. You start to become free neutrons and electrons. You get nuclei, you get ions, and if you're going to the atmosphere, you can even get heavier elements like hydrogen, helium, and carbon. You typically don't really have a lot of muons down here anymore because the chemical thing of the electron is not high enough. It's lower than the muon mass, so you typically don't actually see muons down there anymore. All right, so that was the wrong direction. So that was the inner part of the neutron star. On the outer side, we have a strong magnetic field, a magnetosphere. The magnetic field can be as large as 10 to the 15 Gauss. close to the surface. And that's something that Josh is going to talk about a little bit more about the exact details of the magnetosphere. But basically, you have a very dense core with a lot of neutrons, protons, electrons, and then you have a magnetic field around it that is very strong. Now, there are a couple different types of neutron stars. Generally, you can divide them into isolated and those that live in binary systems. Luckily, Wikipedia has a relatively good summary about all the different types and subtypes of neutron stars that we know of. The main categories are radio pulsars is one of them. They're pulsars. They rotate with around about once every couple of seconds. They do emit a lot of radio emission. And this emission is typically powered by the loss of rotational energy. The other main category we have is magnetars. Magnetars are relatively young neutron stars that are known to have a very, very large magnetic field. It's magnetars that actually reach these really high magnetic fields of 10 to the 15 Gauss. Most other neutron stars are around 3 orders of magnitude lower, just around 10 to the 12 Gauss, somewhere around there. Magnetars also have a lot of emission, but in this case, it is actually powered by the decay of the magnetic field, not by the loss of the rotational energy. And that also has why magnetars have a relatively short lifetime in terms of that emission. Their active life is only about 10,000 years, and that's until the magnetic field has decayed. Then the other main type of the isolated neutron stars are those that are relatively quiet. They're especially the type that is radio quiet, and that's also X-ray dim. So they don't have any emission either in radio or in the X-ray. Now, of those radio quiet and X-ray dim neutron stars, we know of exactly 7, which I think were all measured around, or all found around 20 years ago. Those neutron stars are all relatively old. They're about 100,000 years, a couple 100,000 years old. The surface temperatures, because they are so old, are also relatively cold. They're only about just below 100 eV typically. And the distance from us is also a couple 100 parsecs. Huh? The age is determined typically, there are 2 main ways. The one that's unreliable is by looking at the spin down, how the rotational energy changes, the rotational period. The more reliable estimate, and that's how people know they're roughly 100,000 years old, is by measuring the radial velocity and tracing it back to the origin where they could have come from, because you do still see like the remnants of where they were created. And that's typically how it's being estimated. How the radial mode is estimated, the radial velocities estimate is rather complicated. You can look at like the bulk waves and so on. I don't know much about it, how exactly it's done, but it's basically by tracing it back to its origin and knowing their velocity. All right. Then on the binary front, there's a whole bunch of different types. All of those are pretty much also pulsars, but in this case, they are mainly producing X-rays. And that in this case, the radiation is powered by the accretion of the various binaries. And all these different types are just different, binary types. Some are more with horizontal Brent stars and so on. So there's a large variety on depending how exactly it accretes. The properties of the neutron stars varies widely. That's also where you have your millisecond pulsars, etc. So that's basically summarizes what a neutron star roughly is. So what does it have to do with axions? Now, there's a couple of things you can do with axions. First of all, you have a really, really large magnetic field. And as we all know, axions like magnetic fields, and in particular, they like to convert to photons in the presence of a large magnetic field. So the first thing you can think of is just plain axion conversion, which is just illustrated here. And we can basically think about what we would get if we would observe that conversion, and it would show up as some monochromatic radio lines that we can look for. Now, the other option is we can actually produce axions in the central core. And given that axions don't really interact with the rest of it, those axions would just escape the star. They would carry away energy, and they would eventually cause some anomalous cooling of the neutron stars. So by looking at how neutron stars cooled, how hot they are today, we can also then think about how to constrain the axion from just the neutron star cooling curves. And then the third option is the combination of the both. You can produce an axion in the central core, but instead of it just completely leaving, you can think about it also converting in the magnetosphere. And in this case, it does not produce radio photons, it produces X-rays, so much harder, which is just because the energy is basically set by the core temperature where they were being produced, which is of order keV, and that translates into hard X-rays. Or if the neutron star is really young and the temperatures are very hard, it could also be soft gamma rays. So now I think it's useful to just go through them one by one. And the very first one will be axion conversion, and that's where Josh is going to jump in. So I think.
So this is the stick. This is a huge stick. All right, awesome. Okay, so this is well, it's broadly titled, and you can see we've sort of just smushed some talks together, but we'll bear with it. Here is a little bootleg ET. ET is a trademark, so I can't actually use that, but I can use this odd clip art that somebody produced at some point in time. So yeah, I'm going to tell you about looking for monochromatic lines produced from axion conversion at neutron stars. And so this is really some work, at least my contributions here. So an early paper where maybe we didn't know super well what we were doing, and a more recent follow-up where we think we're really starting to get the signal and the data analysis techniques down. Okay, so I should also point out before I really dive in, this expression has two typos, and Malte did not see my message about the corrected slides. So I'm just going to go ahead and put the expression up on the board so that you can see where the axion is actually coming in this process. Okay, so you should totally ignore this, and you should pay attention to this. Good, but basically the point here, so Malte's already told you that axions are able to convert to photons in the presence of magnetic fields. But what does that process actually look like? Well, we can start with Maxwell's equations, we can couple it to a Klein-Gordon equation, and then we can identify the part that's relevant for that conversion process in the presence of a magnetic field, and it looks something like this and this. Okay, so the point is you can see that there is this mixing, and the mixing is coming in through this term A, where A is our axion field, and B is our external magnetic field. And so if you asked about like the effect of this mixing, which would be to say, okay, if I have a background magnetic field and I have some axions that are present, I can go ahead and I can source some electric field component, and that ultimately look like a propagating electromagnetic wave with some power associated that I can go and try to, you look concerned. The displacement field. Yeah. This is, I'm pandering to Alex, who I'm missing in the audience now. Alex likes things to have their constitutive relations built in. So yeah, good. This is something that Alex Miller, who's here at the workshop, has thought about quite a bit as well. So good. You could think about trying to solve this mixing, and generically you will get some axions that are converted into electric field. But that's maybe not so interesting in most scenarios. The reason for that is you can think about the axion. It's got a mass associated with it, and the photon does not. And so if we said, what do the wave-like solutions for those different fields look like, we'd see they're essentially mismatched. And so I don't expect my axion to typically produce lots and lots of electromagnetic power, just because things are going to average out incoherently, ultimately suppressing the sort of signal that I would get. Now, one way to sort of to beat this limitation that this conversion is essentially kinematically suppressed is to look for an environment where you can give the photon a mass. And so one environment that you can give a photon a mass happens happily to be around neutron stars. So the point is that around neutron stars, you have some appreciable charge density that's going to endow the photon with a plasma mass. And so here what I'm plotting for you, this is coming from a very simple model called the Goldreich-Julian model. And it's essentially saying, okay, if I have a neutron star, that neutron star is described by a rotational axis and a dipole axis, which may or may not be misaligned, that I can talk about the time-varying electric and magnetic fields that are associated with that configuration. And then I can ask, what is the charge distribution that actually supports such a configuration? So I can go out and I can work out under the assumption that the neutron star magnetosphere is a perfect conductor, what that charge density is. And here for some benchmark neutron star parameters, I'm showing you that charge, or essentially the plasma mass endowed to the photon by that charge density as a function of radius. And what you'll see is, okay, as we might expect, far away from the neutron star, the plasma mass is quite small. As we get close to the neutron star, the charge density increases, the plasma mass increases up until this point where we hit the neutron star surface. And there, okay, it no longer makes sense to start talking about free charges and plasma densities, of course, since we should really be worrying about what's actually inside the neutron star. So we're just going to cut ourselves off there. But the point here is that we're realizing plasma masses in this neutron star on the order of 1 to 10 microelectron volts. And so for an axion that has a mass of 1 to 10 microelectron volts, we actually have some unknown mass. We can actually get a matching, at least at some radius, where the mass of the axion and mass of the photon are equal. And there we have sort of a resonant conversion process in which we much more efficiently convert axions to photons, and we can hope to get a more enhanced signal. So the picture you should have in your mind is that axions are infalling. They encounter the resonant conversion radius, so that location where the masses are matched, and then they're converted into outgoing radio photon emission. Cool. Okay, so this turns out to be quite a complicated system to actually make signal calculations for. And so what I'm going to start by doing is telling you the very rough first order one-dimensional solution for what that conversion process looks like. So if you take your Goldreich-Julian model magnetosphere, you turn the crank, you integrate power over the surface of that neutron star, you can say, all right, I can calculate my radio power emitted, and it's going to factorize into really 3 pieces. So of course, there's the normal particle physics dependence, which is to say I have some dependence on the axion-photon coupling and its mass. I also have some dependence on the astrophysical environment in which this is happening. So of course, I want to convert axion dark matter, and so I'm going to do better at producing power if I'm doing that conversion in a location that is more dense in dark matter. It's also helpful to have that neutron star closer so we get more power from it. And then very roughly, we could extract the scaling dependence of the conversion power associated with the neutron star's magnetic field strength and the period of that rotating neutron star. And so maybe unsurprisingly, the power that we get out in radio is going to scale, it's going to increase with increasing magnetic field strength, and maybe slightly less intuitively, with longer period neutron stars, we also get a stronger signal. So that's just a statement about the total power that comes from this radio emission. Another question you would reasonably ask is, what is the spectral morphology of such a signal? And so for understanding that spectral morphology, you can understand it at a basic level is just coming from energy conservation. So the point is the axion is falling into the neutron star. We get a photon, that photon makes its way out. The energies at infinity need to match. And so the energy of the axion, or the mass of the axion, is essentially going to set the energy of the photon that's outgoing up to some corrections. And so one of these corrections is going to be, of course, just the velocity dispersion in the galaxy. So we might expect something like a monochromatic line with an intrinsic width of about 1 part in 10 to the 5. And so that's actually quite helpful because at a statistical level, it's much easier to detect lines than it is broad continua. Not to mention, it's a lot easier to convince yourself that you've actually discovered a line rather than claiming you've discovered some excess continuum. So maybe at a sociological level, or at least how you convince yourself that you've modeled the system correctly, that this is a line is going to give us a better chance at setting a good limit and maybe making a detection as well. Okay, so I told you that that was a pretty crummy way of understanding the signal calculation, and this is something a lot of people are working on. Malte, oh, good. I just want to highlight that there are like 10 papers as of the end of 2022 that are all considering different aspects of this signal calculation. So I want to give credit to all the relevant people. Okay, so the way in the work that I've been pursuing, we calculate the signal is actually through a ray tracing approach that's going to try to combine as many of the relevant aspects from those works that are doing the actual signal calculation. So what do we have? We have our axions that are falling in. Here's a little sketch of what the conversion surface for this neutron star actually looks like. It's not a perfect sphere. It has some non-trivial geometry associated with it. But when these axions encounter the conversion surface, they're going to become photons, at least with some small probability, that then propagate away. So one thing that's interesting, I think, is actually that there are two hard parts of this calculation. One of the hard parts is what does this conversion probability actually look like? And although this has been studied in one dimension, so basically assuming that the axion has a radial trajectory, this has not been particularly well studied in a full three-dimensional system like this rotating neutron star. Another hard part of the calculation is that the same plasma mass that actually allows this resonant conversion process to happen is also going to lead to some non-trivial effects in the photons propagation away from the neutron star. So one way of understanding what that plasma mass is effectively an index of refraction. And so here what I'm plotting for you is the photon trajectory after the time of conversion, in which it's strongly refracted through this magnetized medium. Good. So we can perform such a calculation. It depends on a lot of Monte Carlo, but essentially what we do is we shoot lots and lots of axions towards our neutron star. We model the conversion process, we model the propagation away from the neutron star, and we track how much photon ultimately escaped and what location on the neutrons on the surface at infinity does that photon reach. You have a question? Good. I'm sorry, I didn't say this particularly clearly. Yeah, I'm assuming a dipolar magnetic field for the neutron star. There's, I think, overwhelmingly strong evidence that that neutron stars do have at least dipolar magnetic fields. Although it would be a reasonable question to ask, is there a quadrupole? And this is not so well studied, really. Well, one in this context, but also quadrupolar fields fall off rather quickly, and so it tends to be hard to study the precise details of these field distributions through at least observation. Yes, good. And the reason this, it's the magnetic field strength, yes. Yeah, sorry for not explaining that better. Good. So like I was saying, shoot axions in, get photons out, track where they end up in terms of the sphere at infinity, and sum up their total power and the amount of frequency shift that they experience from that axion rest mass as a function of the refraction through this moving medium. And we can make a plot that looks like this. So I've extracted on this pixel right here, and I'm making you a plot of the power distribution. So this is in some arbitrary units, and this is the bandwidth, or rather the relative bandwidth as compared to the rest frequency of the line. And so maybe it's a little bit hard to see, but this number here is about 10 to the minus 5. So again, this is more or less consistent with the amount of broadening of such a monochromatic line that you would associate with the velocity distribution of that dark matter. Yeah. This conversion is outside the neutron star. Yeah, I'm sorry. Yeah, the point, I am totally agnostic as to what's happening inside the neutron star. I don't know how to talk about a plasma mass inside the neutron star. Good, I see the confusion. Yeah. Yeah, and so this, say again? When does it come out? It can take quite a long time. It's not going to propagate on a, it experiences refraction as it goes through the plasma. So that's, that's like this. So, you know, if some photons will not escape. That is true. Yeah. How thick is this plasma? Yeah, good. So good. So if I consider this the center of my neutron star as the origin, these conversion processes are typically happening tens or hundreds of kilometers away from the neutron star core. Yeah, as compared to maybe the 10-kilometer roughly radius of the neutron star. So you're well outside that range. You probably don't trust your calculation as much when you're predicting that the conversion would happen right at the surface. That I think. Yeah, potentially. Yeah. Good. So one underappreciated aspect of this calculation is that so far, at least in these 1D treatments, people have talked about this as a 2-level system. It's not really a 2-level system because you're solving classical equations of motion. But if you can try to consider this process as like an on-the-spot conversion, you can try to treat it with something like the Landau-Zener formalism. And so one extra tricky aspect of this is that if you have a super high conversion if you have a low conversion probability, everything goes through pretty directly, and that you have your conversion surface. You convert with some small probability. Those photons propagate a little bit, but essentially they're encountering a barrier because now the plasma mass is increasing as you get closer to the neutron star. That plasma mass is then larger than their energy, and so they can't propagate inward anymore. They reflect. During that reflection, they have to propagate back through the conversion surface, but because the conversion probabilities are very small, that's actually okay. We essentially get an unmodified signal in that case. Now, what's quite a bit trickier is actually if you think you have a really good neutron star that's going to give you large conversion probabilities, well, then you should be concerned. So let's imagine that the conversion probability at the surface is 0.5, 0.9, something close to 1. Well, actually, you're going to convert with high probability from an axion to a photon, experience the same reflection, propagate back through the conversion surface, and more likely than not, be converted back to an axion that you can't detect. And so whether you're in the strong conversion or weak conversion regime is something that we've been thinking carefully about lately. And so in terms of like relevant coupling strengths as compared to flux densities, flux density is really the unit of measurement for these radio telescopes that we're going to use to try to make measurements of potential spectral lines. As you see, actually, if I plot the flux density of radio emission as a function of axion coupling, these are just two different lines, different assumptions about the neutron star modeling. You see that around 10 to the minus 12 inverse GeV, there is a suppression even of that conversion flux. And so that's just something that we're going to need to bear in mind for later. Yeah. Good. So I'm going to get to this in a second. So let's see if I can answer that question later. How far what? From us? Great, we're going to get to that. Yes.
Sorry, but if you say that the region of the conversion is of the size of kilometers,
Sure.
Then the photon will undergo per creation, scattering. How do you expect to have a line? This is what.
Good.
Okay, we have.
Yeah. Okay. Good. So these photons are not. These are not so energetic photons. We're talking about like micro-eV energies. I'm not sure I don't expect those to be pair created.
Microwave, I say photon to say microwave. I mean the electromagnetic. Okay.
Yeah, and so
it will in a plasma.
Yes.
Probably will not remain a line, right?
It will not remain a perfect line. That's true. And so part of the point of the signal calculation we're doing is to actually calculate the propagation and frequency dispersion of those photons. And we find in the medium of the plasma. And we're finding that the line broadening associated with those plasma effects is not, well, it's essentially of the order of the velocity dispersion, and which is nice. turns out that that's
Just
not
the velocity dispersion.
well, the velocity. So what you should expect is you should expect a line that is already initially broadened by the velocity dispersion.
This is
Then,
okay.
then once you then you consider the plasma broadening on top of that velocity dispersion. It turns out that these are similarly sized effects, and so you maybe double the line width as compared to the intrinsic width associated with velocity dispersion. But it's not a huge impact on the.
And I have also a second question.
Yeah.
So in previous slide, you have put that the probability of conversion is 1 around. You have PA gamma.
Yes, good. Yep.
Is order.
Yeah.
And even in a previous slide, you would show that the trajectory would cross twice.
Yes.
So it will go through twice to the same region with some magnetic field and some plasma density.
Yep.
So you might think that often you have a conversion and a reconversion going out.
Yeah, that happens. And so that's something that I'm at least.
Yeah, here it looks like a reflection. But
yeah, so what you would have expected if there was no reconversion present is you would have expected the flux densities as a function of Ga gamma gamma to follow these dashed lines.
Oh, okay.
But what I'm showing you here in the solid lines is the flux density now associated with accounting for that you can have reconversion, and that can be an important effect.
Thank you.
Yeah.
So these curves are the result of some Monte Carlo or some analytical?
Good. These curves are the result of the Monte Carlo treatment that I was showing you previously for getting the flux at a given pixel. Yep. Excellent. Okay, so one of the things that we need to think about here is what's the best location for us to actually be looking for this conversion signal. And so maybe not extremely surprising is that the best place for us to look for this conversion signal is actually at the galactic center. There, we expect there to be a large number of neutron stars, and we also expect a high dark matter density. Now, the challenge associated with this is that we don't actually know of that many neutron stars at the galactic center. If we did, we would have probably resolved the question of the galactic center excess by now. And so what we have to do is we have to depend on some population modeling of what the neutron stars at the galactic center are actually going to look like. And so what that looks like is we need to start with some initial distribution of neutron star properties, model those properties like the magnetic field strength and the spin period through their magnetorotational evolution, and then ultimately make a prediction with this Monte Carlo procedure that I was telling you about before to say, if I have an ensemble of neutron stars, what is the expected forest of lines associated with axion conversion? And so what I was showing you in that previous figure actually was just two different population synthesis models. And so I'm going to try to really bracket the uncertainties associated with that population modeling with an optimistic and a pessimistic model. Essentially, you can understand the difference between the optimistic model and the pessimistic model as the question of what happens to magnetic fields over the lifetime of a neutron star. We know we want large magnetic fields, and the question of how those magnetic fields evolve is an open question. So in our optimistic model, we say, great, we have a neutron star, it's born with a potentially very large magnetic field, and then that magnetic field strength is frozen in. In our pessimistic model, we allow that magnetic field to decay. And so there have been some studies of this by various neutron star modelers. What does seem extremely pessimistic is the idea that your magnetic field is decaying with a lifetime of around 10 megayears. And so we adopt that pessimistic benchmark for magnetic field decay in our conservative model. Good. I don't want to take too much time away from Malte. I'm sorry. Yeah. Yep. No, yeah, so I think really the galactic center magnetar is the only one that's coming to mind for me. It's maybe not super surprising that we haven't discovered these neutron stars, as sort of what you care about there is the probability that the beam is pointing at you. And so the beam doesn't have a very large solid angle. We can discover pulsars because we see that pulse in the data. But if they're not beaming towards us, they essentially look like dim sources, and then they're quite hard to pick out. Yeah. Okay, so if we go and we measure a radio spectrum with a telescope, we can try to look for these lines. And so here I'm showing you some Monte Carlo associated with one of these neutron star populations for what the forest of lines looks like. And so here you see lines that are, so there are individual lines such as these that are appearing in the spectrum. But then what we also have to remember is each one of these neutron stars is moving with some peculiar velocity. And so there's a line with intrinsic width of about 1 part in 10 to the minus 5, but that is broadened by about 1 part in 10 to, broadened by 1 part in 10 to the 3 associated with the Doppler shifting of those neutron stars. So what we can do is we can actually look at these spectra and we can ask, like, what's the best way for us to go and detect one of these lines? And the way is to find usually the narrowest line feature. These broader lines, these are stars that have more broadening associated with plasma effects in the magnetosphere, and so they're not quite as detectable. So we want, to look for those narrow lines, and we want to look for them with very long exposures that are frequency resolved, so we can actually make out that line-like morphology. Good. And so this is a challenge because if you think about what you want to do, you want to look at many, many axion masses because the window over which a signal could appear is going to be set by the axion mass. So really you need sort of frequency resolution of 1 part in 10 to the 5, but you need to consider this over maybe a decade of axion masses, at least in the range relevant for these radio searches. And so if you said, I want frequency resolution of 1 part in 10 to the 5 over tens of gigahertz, then radio astronomers are going to tell you you have a problem. That is a challenging data processing problem, let alone a challenging data set to store on disk. You're talking about something that's hundreds of terabytes, if not petabytes. But we're sort of lucky in that there are people out there who are already looking for ultra narrow radio signals, and that is people who are thinking about SETI. And so the idea behind SETI really is to look for radio lines, because if you think about your AM radio has a central frequency spike on the order of 1 part in 10 to the 6 relative width, and that's what helps you find the actual channel you're supposed to be looking at. And so the thinking is, if we can do 1 part in 10 to the 6 terrestrially, surely some aliens that want to be discovered can do at least that. And so the Breakthrough Listen project is a SETI search that has essentially a GPU cluster hooked up to a radio telescope so that they can do super fast data processing, producing a data set that has frequency resolution of up to 1 part in 10 to the 9. And so that's where the resolution that they do their analysis at. They think we're simple for doing 1 part in 10 to the 5. So the Breakthrough Listen people are also sneaky. They nominally, they're supposed to look for aliens. That's what they got money for, but they also want to do complementary science. And so one of the searches that they've done is they've just done a deep survey of the galactic center. And so here I'm showing you the tiling of the galactic center that they performed with tens of hours of survey time. And so what's going to be relevant for us here is this A00 field, which is the galactic center. Let me keep moving. And so if you trust us that we downloaded the data properly and analyzed the data properly, then we can go and we can say, did we find lines or did we not find lines? We didn't find lines. And so we're going to set limits on the axion photon coupling. And so here is our the axion photon coupling limit associated with that conservative scenario of rapidly decaying magnetic fields. And here is the sort of more optimistic scenario associated with magnetic fields that are frozen in from birth. And one question you might ask is, like, if I told you one was conservative and one was optimistic, why are these constraints so similar in sensitivity? And this is for the reason that at about 10 to the minus 11 inverse GeV, you're sitting within this regime where back conversion is important. And so the response to the axion coupling, or really to the neutron star properties, is essentially flattened out. And so in this regime, at least, the conservative model and the optimistic model give us similar constraints, and that makes us feel a little better given the associated uncertainties with astrophysical probes like this. Yeah. The gray line is cast. Yes. Yes. Yeah. So, good. So that was the search we did in data, and now let me just say something about where we think we're going to go in the future. So that was using the GBT telescope, and so these limits are living right here. Some instruments that are online right now and that we could think about using for present day searches are MWA and HERA, along with telescopes like Meerkat. And so these would require qualitatively different search strategies because these are radio interferometer arrays rather than a single dish radio telescope like GBT. But what's really exciting to me is the prospect of SKA. And so with SKA, the future square kilometer array, we get much better flux density sensitivity. That's the first selling point of SKA. And then as relevant for this axion search is that once you're looking with that good of sensitivity, you're no longer in this regime where you're suppressed by the back conversion. And so you pick up quite a bit of sensitivity by going back to the regime where your flux density, your expected flux density of these lines scales quite strongly with GA gamma gamma squared. And so we expect to be able to set constraints at about 10 to the minus 14 or 10 to the minus 15 inverse GeV, which I think is pretty interesting in that this is an astrophysical probe that could potentially be cut into the QCD axion line. I think also that the data analysis strategies and the way you can leverage the resolution both spectrally and spatially of these telescopes is something that we can think about quite a bit more and hope to get more sensitivity out of. And I would be extremely happy if that line could get pushed down to DFSC sensitivity, in which case you'd have a probe complementary to instruments like Haystack or ADMX of this axion dark matter hypothesis in the sort of 1 to 10 micro eV mass range. Okay, yeah. Why are these flat? Good. So these this is just these are things like the varying beam width of SKA as a function of frequency. So if you believe that your signal is going to live all within like the very central pixel, which is not quite the truth, but to good approximation it is, at SKA, as you go to lower frequencies, which we can't access here in GBT, your beam gets wider, which means you're bringing in more background, and the strength of your limit decreases somewhat. There's also just a frequency dependent gain in SKA. That means it's less sensitive about amplifying flux density that's incident on the radio antenna into power that's recorded by the receiver, and so that's baked into that projection as well. These, I should point out that these. There's also, of course, the variation in whether a neutron star is actually converting and how strong that conversion process actually is as a function of mass for fixed neutron star parameters. So there's a lot of things baked into that line that make it vary. I should also point out that like our GBT constraints are certainly not flat either. We just flattened them here for the sake of a clean looking image. Yeah. Okay, so that brings me to the end of my part. I am sorry for, oh, yeah.
My question was, why does the conversion probability depends on the rotation period of the?
Yeah, so this comes out of the Goldreich-Julian model. And so what you'll find is that the charge density is a function of both the magnetic field strength, but also the rotational period, because this is set in how fast the fields are changing at a particular location as a function of time, and then what charge distribution you need to support them. So the effect of changing the plasma density profile is then to shift the distance from the neutron star at which the conversion occurs. But now because you have a dipolar field, if you move that conversion closer to the surface, you experience a stronger magnetic field, and that leads to a larger conversion probability. And conversely, if you're farther away from the neutron star, weaker field, weaker conversion probability. It's the same G squared, B squared, L squared as in everything else. All the challenges are really associated with calculating what that L is, which is you should associate as like sort of the length scale over which this mass matching is good, and then that B being the magnetic field strength evaluated at the location of that mass matching. Yeah. Yeah, good. So I think we have not studied the role of turbulence. This is something I am ramping up to do now, is to do really like 3D simulations of this conversion process and hopefully more realistic magnetosphere environments. So people like Alex Miller, but then also Sam Whitty have worked hard. Alex is not here, which is a shame. But they've worked hard at understanding like what are the cutoffs that you are you would associate with the magnetic field or the propagation of photons not being, extremely slowly varying, and how should you expect that to change your conversion probability? This is baked into that Monte Carlo procedure, but it's also certainly true that there are effects that could have been missed that would either suppress or enhance the signal. Yeah.
Speak louder.
Yes. Mm-hmm. Yes. Yeah, good. So what this is based on, a variety of astrophysics. Okay, so for the population synthesis models, what this comes from is like the ATNF catalog. And so we have a distribution of measured P and P dot for stars that are not at the galactic center, but at least ones where we hope to reasonably well understand their age. And so from P and P dot, we can also infer their magnetic field strength. So the population synthesis models are calibrated against producing an expected population that looks like the population that we do observe, again, away from the galactic center. So what you then have to do is you have to say, all right, if I believe that I can model the distribution of pulsar properties at birth, and that I can evolve them to their present day age, then what I need to know is I need to know what is the birth rate of neutron stars at the galactic center. This is something that astronomers who are studying stellar distributions near Sagittarius A star care about quite a bit. And so we're able to pick up those models. And essentially what they amount to is, looks like there was a fair amount of stellar formation followed by neutron star formation over the last 30 million years or so. And since that's on the order of this conservative model where we say the magnetic fields are decaying, there's not too much suppression. Yeah. Yeah, so they're different because it turns out that the photon coupling that we can constrain, the photon coupling that we can constrain in either scenario is living in this regime where the conversion probability is made can be as large as like 0.5. In which case you have some strong conversion, but you also have strong back conversion. And so that was this plot where the flux density as a function of GA gamma gamma becomes quite flat. So since both happen to be probing where the flux density as a function of GA gamma gamma is flat, we don't see a super big difference in the limits that we set under either modeling assumption. Yeah, so your flux density sensitivity scales like square root bandwidth, and then your coupling sensitivity scales like bandwidth to the 1/4. And so that's maybe not like a extraordinarily fast rate, but if you compare the difference, I'll take the factor of 5 to 10 any day. Yeah. Good. So we have not. In principle, you could leverage polarization information in an analysis like this. There should be some polarization dependence in the conversion flux. This is not something that we've actually included in this analysis, in large part because, well, this hasn't been studied particularly well, I think, at a theoretical level, but also the radio telescope we're using doesn't record polarization data. It only records absolute intensity. So we don't have all the Stokes parameters we'd like. And so not relevant here. It could be relevant for SK in the future, though. But no, they're at the galactic center. So like 8 kiloparsecs away. Miljansky, but yeah.
Other questions for Joshua? No, then we'll go on.
Okay. Malte, I've used all your time. I'm sorry.
Which speaker?
All right, I'm back. So everything that just can't speak anymore. Everything that Josh just talked about happened outside the neutron star. So let's move inside the neutron star and think about how to actually produce axions. Now, one of the main production mechanisms of axions is just plain old Bremsstrahlung. So you just have your neutrons and protons, and you just radiate an axion after some pion exchange. Now, what is shown here, and I apologize for having put on rather lengthy equations, are the emission rates of the axion from the different Bremsstrahlung processes. But I think it's relatively instructive to actually go through the different terms that enter this. So after some normal just prefactor, some numerical prefactor, of course, your emission rate depends on the couplings to nuclei of the axions to nuclei. That's relatively straightforward. Then you have a couple of factors that are parameterized through the Fermi momenta. That's basically just encodes the density dependence of that emission rate onto from the neutron star. Now, the second term is then the temperature dependence, which turns out to be to the sixth power. And then there's a couple extra factors that are a little bit more complicated. There is one short range correlation factor. That's just because the actual length scales involved in these processes, because every surface dense is relatively short. So you get some corrections there that are just coming from the Yukawa potential at short distances at short range. Then there's another correction factor that just comes from multiple pion exchanges. That one is relatively straightforward. Then there's another factor here, which is just written as gamma. This is just a correction from the fact that this takes place in a rather dense medium and not in vacuum. And this typically ends up being some factors of effective mass for the neutron and the proton. And then the last factor is another correction factor. It's due to the superfluidity. This factor is 1 if there's no superfluidity, and it's going to be something less than 1 if there's superfluidity. And the reason for that is just if you have superfluidity, a lot of your neutrons and protons will be bound up in Cooper pairs and are not actually free to perform the Bremsstrahlung. So you have this extra suppression factor over here. Now, Bremsstrahlung is not the only process that happens. The other one that happens is if you have superfluidity and your temperature is below some critical temperature, you can actually also produce axions just from the formation and the breaking of Cooper pairs, which is shown over here. And those rates can be computed as well, but I'm not going to go through those. I would need to refresh my mind on that, where exactly that comes out of the equation. What was the question? Sorry. Why this is t to the 5 and not t to the 6th power?
But you know, the power of t is always easy to get. So even when you change from degenerate to non-degenerate, for example, in Bremsstrahlung, you change from like 3 to 6 in the or something. So it is. And all of these things you want to black. So you have t to the 6, that should be rescaling of an
Yeah, I can follow up with you afterwards. I know it's in our paper written somewhere, like where the calculations are coming from. We can trace that down. It should be relatively straightforward to figure out. I just don't know it by heart anymore. It's been about 2 years since I did some of these calculations. Sorry, what? Not entirely sure, actually.
I guess the question. Okay, no problem. The question, I guess, is why do you have a suppression if a proton and neutron build up a Cooper pair?
You mean for the Bremsstrahlung?
Yes, at least this is my question.
Right, well, because you need to have free neutrons and protons. You can't easily scatter off the Cooper pair itself, at least not in that way. yeah. All right. So now the thing that I want to point out, this process from where you radiate from the breaking of Cooper pairs and the formation is actually the dominant form of radiation. So you can easily see that in the prefactor, this is around 10 to the 13 for those. Whereas if you go back for the axion productions, it's 10 to the 12 around. But of course, we don't know whether the core is actually superfluid or not. So it's one of the uncertainties of neutron stars. Now, the reason we want to talk about compute how many axions are being produced is because, of course, it affects the cooling. Neutron stars have three main ways of cooling. One is through the emission of neutrinos, one is through emission of just photons, and then the axion is the third one. Now, a very young neutron star cools mostly through neutrinos, which is coming through thus the modified Orca process mostly, which scales like T to the 8. At late times, a neutron star cools mostly through photons, which is just a normal blackbody spectrum that scales like T to the 4. And the axion normal Bremsstrahlung emission is T to the 6, so somewhere in between. And for an axion mass of around 16 MeV, turns out that the main cooling mechanism for a neutron star that is a couple thousand years old, 10,000 years old, is actually through axions. And that is relatively good news, because if you remember where the magnificent sevens are, they were all around a couple 100,000 years old. So they're sitting right here, which means that while they're today actually cooling mostly through photons, they have undergone a relatively large cooling period where the dominant cooling mechanism is axions. So we can use those magnificent seven actually to place bounds on the axion emission. Also, if you notice the little infinity here, that's just because all of the quantities that we're looking at actually need to be redshifted to infinity because of the relatively large gravitational potential that the neutron star has. All of these quantities actually redshift quite a bit. Now, so that's exactly what we did. We looked at the magnificent seven, and you might count that those are only 5 and not 7, and that's just because we don't actually have good H estimates for 2 of them. These H estimates are kinematic estimates, which is what I addressed earlier. So those are really coming from tracing back to the origin, which are the more reliable way of estimating how old those are. So what you can see here are 2 different cooling curves. One is just a null hypothesis in case you have axions. In the other case, we assume that we have an axions. Those cooling curves are obtained by just using the NSCool code, which just solves the energy balance and transfer equations in one dimension. And we just modify those in order to include also the axion emission. So good. We marginalize over all of these different parameters. So what we show up here is actually the best fit curves for a 16 MeV axion. And we allow the best fit to vary over the axion mass between 1 and 2 solar masses, and we don't have any, it's a flat prior for that. And the axion mass is not, yes. Mm-hmm. The other method, I think, actually yields like they're more like a couple million years old. But for this particular these particular neutron stars, that measurement is relatively unreliable. Like, for example, if you assume actually take that age, like there's no way to actually find any sort of random. There's nothing around where they could originate from even. And kinematic ages are much more reliable in that case, because we do actually see in that age like where they were originating from, where they're coming from. Yeah, and what you have to do in this case is, because neutron stars are so unknown, so many properties, the only way to actually get a solid bound is by really marginalizing about all the different uncertainties that we have, which includes the axion, the mass of the neutron stars, and includes some of the composition of how many light elements you have in the atmosphere. It also you need to marginalize over different equation of states, which tells you how dense the neutron stars are and their exact composition. And you also have to marginalize over the superfluidity models, including assuming that there is no superfluidity. And these marginalization parameters are also the reason why some of these curve, your assumption that you have an axion is actually higher than the no axion hypothesis. That's just because those neutron stars just have in the best fit a different marginalization parameter behind it. So it's just a different axion, for example, a different neutron star mass in one
There
case
is
than
another
the other.
question.
Bottom left, this one. If I remember correctly, I think the reason in this particular case is, and I would need to look that up again to refresh my mind, is that this one has a higher temperature overall, such that some of the processes for the superfluidity don't actually switch on, because you need to be below the critical temperature for them to actually work. It usually has something to do with that certain processes that rely on below or to be below or above a certain critical temperature switch on and off. And that's most certainly what happened here. I just can't remember by heart which process exactly that was in this particular case. Yes. So for the fit, well, we just have 5 data points. We do run these set of just cooling curves for various different parameters. And then we just do a log likelihood analysis to find the best fit model. And we do marginalize, of course, for like the neutron star mass, we keep it floating for every single one individually, but we keep the same equation of state for all 5 of them, but then we marginalize in a global fit over those. It's just a log likelihood. Yeah. Yeah, we profile. It's a profile log likelihood, yeah. Yeah, no, we did not.
We're doing likelihood analysis but then we want to achieve limits of function that have a proper coverage using a lot of so it's not. Yeah, no, that's very good. Maybe the other thing is because when you say marginal, I thought that maybe calculate first marginal likelihood, because sometimes when you profile, I mean, of course, you can take a certain power this way, but from a practical point of view, this sometimes underestimates a little bit. Yeah, so I think because we do the proper procedure, our links formally have the proper coverage, and so things to go back in this modeling, not so much the results.
Yeah.
Another question.
Sorry, what can you? Oh, yeah, we did also look at a couple other neutron stars. I don't remember exactly which ones they were. Yeah, like the reason is you want to have neutron stars that are relatively old that have gone through the cooling period of axions. Yeah. Yeah, neutron stars that are too young, they mostly just cool through neutrinos, so you don't have any sensitivities to axions in this case. There are 1 or 2 others that are also a couple tens of thousands of years old. We looked at them. As far as I remember, they didn't have any like big statistical significance. They didn't really contribute to the likelihood at all. So these are the 5 we really focused on at the end. Yeah, and in the appendix to that paper, we show a lot of different variations and systematics and so on. Yeah, exactly. It's t to the 8 with this t to the 6.
One more question.
There was this paper by Hamaguchi et al. And they found the limit on the axion neutron coupling, which I think is stronger.
Yeah, but that was before the paper actually. Yeah, it was before. I think I talked to you guys about
That one is stronger.
Yeah.
There was some comment in the text that the estimate of the age of this classifier is not high.
Of Cassiopeia's, you say? Or yeah, how old is Cassiopeia? I'm not entirely sure. Oh, that's Cas A. Okay, yes. Yeah, that one is. So Cas A is too young to do an analysis like this. I think what you do is actually you look at the slope because it's so young and cools so rapidly. We can actually measure the slope of this. And I think the problem with doing an analysis like this is at this early age, it really depends on the details of your equation of state and your superfluidity much more than it does for these young ones. And there's a whole bunch of equation of states that are just very offset. So like your systematics on how you treat that, it's a little bit more complicated to get the details right there. So that might be the reason why it's stronger is because it's, like there are systematics that we just are very poorly understood in that case. It's my guess, but I would need to look at that paper again, what exactly they did. Anywho, so we did our analysis and we marginalized over all the different parameters and uncertainties to get the most robust limits we could get. And you can interpret it in various different ways. For a KSVZ, it means that the axion mass needs to be below 16 MeV, which is also why these always I showed at 16 MeV. For the DSF that, it depends on ton beta because that modifies what your couplings to the to protons and neutrons are. The limit is most of the time slightly weaker than the supernova limits, but they're also probably a little bit more robust than the supernova limits. But overall, they're very similar and they beat IAXO for small ton beta as well. And then for the ALV, you can of course express that for very low, asymptotically low axion mass. So you can just, transfer it as a constraint onto the individual couplings to protons and to neutrons. All right, so with that, let's just move over to the last part. So with axion production and then conversion. Now, in this case, we produce axions and we convert them somewhere in the magnetosphere, and that leads to typically a hard X-ray. So for the really young ones to soft gamma rays. There are two different approaches to deal with this. The one approach is you look at a neutron star that has a very large signal. Those would be, for example, just magnetars because that's, they're very hot. They produce a very large signal. The problem with magnetars is, of course, they are pulsars. They produce their own radiation. So it's pretty much, given how little we understand about magnetars, it's impossible to actually model that. So we can't use it to actually detect an axion. But what we can do is we can use some conservative assumption that all of that radiation is coming from axions in order to place a bound on axions, which is exactly what this group of people did. So this is one of the magnetars they looked at, and they just fitted an axion signal to it and ultimately placed a bound, which is shown here. So those are two different magnetars. One, and you need to look at hard X-rays. The other one is soft gamma rays. The bound they find here is a little bit stronger than the limit from cars plus supernova. You need both of them, given now that the only thing you can constrain is a combination of the coupling to nuclei and photons, given that you now have production and conversion at the same time. Now, this limit is a little bit stronger. However, what I want to point out, just to be fair, is they actually fixed neutron star parameters in here, and they didn't marginalize fully over all the different uncertainties. In fact, if you change the core temperature a little bit, you very quickly end up with limits that are quite a lot weaker. So really what this tells you is that if we were able to understand neutron stars a lot better, we can really set very strong limits on axion. At the moment, we are basically just limited by an understanding of neutron stars and their dynamics. But it is in principle something that can be done once we hopefully understand neutron stars a little bit better. Well, yeah, they could go either way. Yes, I'm optimistic that, you know, once we know. At least they become more robust either way. Yes. You're talking about this kind of relation, right? Right, yeah. Mm-hmm. All right. Now, the other approach to measure that is to look at neutron stars that have essentially no background, because then you can get away with a small signal. And that brings us back to exactly the Magnificent Seven, given that we expect that radiation to come from hot X-rays, and the Magnificent Seven are X-ray dim, and they only have, at all, if at all, some soft X-rays. So they're essentially background free. So Chris, Josh, and Ben, when they looked at the data from the Magnificent Seven, and there's actually quite a lot of data available, because it turns out a lot of these neutron stars have been used as calibration sources, where they looked at the blackbody spectrum, which is apparently very well defined, so you can use it to calibrate your sensors. And as a side effect, they also measured the hot X-ray spectrum, at least the very beginning of it. Now, initially, the idea was to have basically no signal and to place bounds on it, but that's not actually how it turned out at the end. It actually turns out that pretty much all of these neutron stars showed some excess of some form. And also, they looked at 3 different instruments, 2 from XMM Newton, PN and MOS, and also Chandra, and they also all showed a relatively consistent, especially most easy to see, which is also the one that has the most statistics, is the neutron star 1856. You see very clear access that is actually consistent between all of them. Now, whether that's axions or not, I don't know. It's actually pretty hard to come up with any proper explanation for where this is coming from. Yeah.
You have data points at the beginning, and then these with large error at the end.
Yes.
What are the data points at the beginning?
This is just the blackbody spectrum, the tail of it. So the surface temperature of the neutron star is about 100 eV. So you have your blackbody spectrum that just falls off, and this is the tail of it.
Okay, thank you.
So yeah, you have your black body spectrum. I think it's actually 2 black body spectrums technically. And then, yeah, you have your high K tail, high energy tail that shouldn't be there. Yeah, it's pretty hard to actually come up with any explanations. Like, of course, there could be some systematics from the instruments, like pileup, for example. But given that there are 3 different instruments that see it and they all have different angular resolutions and so on, there's typically some reason why, it's unlikely to be one of them, unless it's a combination that, that just add up to be in different instruments to yield exactly the same kind of systematics. Yeah. Uh-huh. You mean on the y-axis or on the x-axis? Uh-huh. Yeah, I mean, it's a logarithmic. Yeah. It's on a logarithmic scale. So like, you have orders of magnitude more photons up there than in the tail. Yeah, and in terms of physical processes, there might be some that, of course, could cause it. Like people have, for example, suggested that it could be accretion, similar to X-ray pulsars, just accretion in this case from the interstellar medium. But typically, that also comes with some X-ray emission, of which they have none. So it's a little bit unclear what this radiation really is. Of course, that didn't stop us to interpret it as an axion, given that we looked at the data in the first place in order to constrain the axion. So in this case, we might as well fit a signal to it, which looks something like this. So this is just a best fit axion model. We can do that for all of them. We can combine them properly, of course, marginalized over all the different parameters again, and we can come up with a limit. Well, not just a limit, we actually have a best fit region, of course, given that it's an excess, which is sitting just below the chaos plus supernova limit. In this case, we assume that there's no superfluidity, which is sort of the conservative assumption, given that that provides you the least emission. So if you have superfluidity, these bounds would actually become a little bit stronger. And superfluidity in general is actually pretty interesting, because if you look at, I've told you that the rate is higher, but the actual spectrum of superfluidity where it actually emits, so this is the one which is just, the dotted line is just bremsstrahlung alone. Once you have superfluidity, your spectrum actually peaks at much higher energies, which is actually outside of, mostly outside of the range of these 3 data points that we have. So the idea is, what we were thinking about is, of course, is a way to measure these higher energies, because that's where we would expect most of the duration. Yeah, well, we have an exclusion limit, of course, because we can always set one, and we have a 1 and 2 sigma region here. No, so the fit region will never disappear. We'll just move to lower couplings in order to compensate for the extra emission that you have. No, sorry, it would move down. It would move to slower couplings because your emission rate is higher. So you need to have a smaller coupling in order to compensate the extra emission that you have. So that's why it's the conservative assumption is to assume no superfluidity, given that that gives you the weakest signal. But we were somewhat intrigued by the large, signal that you would get at higher energies. So we asked NASA kindly if they want to point the NuSTAR telescope for about a day at this neutron star 1856. And they actually said yes, and we have data, which I'm happy to actually share here. Now, unfortunately, 40 kiloseconds is actually much less than the 1 million seconds that we already have data from the other instruments. So we don't actually have any statistical power to actually say anything about that excess at like the low energies that we see. So the data points over here is the new data, and you can see it's actually a small downward fluctuations, but it's just, you know, a little bit over 1 sigma below 0. And in a sense, those are almost statistically like comparable. Yes, which is here now. Now I show you the entire data goes up to 80 K. Well, the reason we wanted to look at, if you look at this peak, the central peaks are like 20 kV. They're over here, which were outside of the range that we tested. So yeah, that's really like, this aim is not to test just axion with like normal bremsstrahlung. We actually wanted to see if we can see a signal from neutron stars that are in a superfluid state. And if axions exist, we would expect a pretty large signal over here. But as you can see, we don't really see anything except maybe this small data point, but you know, it's just statistics. So what we can use this data for, and that's ongoing work, is to place a limit under the assumption that new superfluidity is a thing in neutron stars. We can place a bound on axions and that under that assumption. Yeah. Well, you might know better, but I would think it's this energy range, right? Yeah. Yeah, tens of kV, exactly. Which was exactly the energy range that we wanted to probe. Yeah, so this is ongoing work, and eventually we'll actually have bounds. We just need to throw in some statistics on this, which is work in progress. All right, now this is the X-ray signature, and I know I'm already half an hour over what I intended to do. The sun is out, yeah. I'm very sorry. If anyone wants to leave, I wouldn't blame them. So I only have like 3 slides left, and that's just about the other signature that you can get from production plus conversion. In this case, you do actually not produce axions in the core of the neutron stars, but there's a different way of producing it, which is in the magnetosphere. If you recall, the axion couples to E dot B. So if you have, and B is relatively large in the magnetic field, so you just need a component E that's parallel to the B field in order to get any sort of axion production. And it turns out that if you have cascades in the magnetosphere from just pair creation of electrons and so on, they can sufficiently screen the field in order to actually have a non-zero component over here and produce the axion that way. Of course, the energies involved here are very different. So the energies that you expect in this case is more like a broadband radio flux that comes off those. Now, for that to actually model that properly, and that's it's not my work, this is a little bit beyond me at the moment. You need to properly model the magnetosphere and figure out exactly how in those vacuum gaps where you do expect to have this proper component in there, you need to model the magnetosphere properly using particle and cell and other techniques to get this component. Either way, that's what some people did, comparing some simple simulations with some semianalytic models. And in the micro EV range, it actually yields relatively strong limits if you look at like 27 different nearby pulsars. And with that, I am actually at the end, finally. So thank you very much.
So thank you very much. Was a very beautiful talk, comprehensive, a lot of information. Are there other questions? We had already a lot. Yes.
So coming back to this neutron star cooling bound, so what happens to the bound if instead of marginalizing over superfluidity, you just assume that there is no superfluidity? Is it, would that affect the bound?
You're referring to these bounds?
Yeah.
So the strongest bounds here are actually also obtained if we don't assume superfluidity, given that that leads to the weakest limit, since that's also your weakest signal. You can see, however, this band over here, that's roughly all of the limits that we obtained by marginalizing of equation and state and superfluidity models are contained within this band. So the weakest, of course, no superfluidity is on the top right, and the strongest one where we have the strongest signals is somewhere on the right. And that one is then actually stronger as the supernova limit and any other limits too, but it's not the most conservative assumption.
Thanks.
Mhm.
But I think
I don't-
Neutron star, like you can keep like if you're well even higher than nuclear density, 10-30 grams per cubic centimeter. I think my condensate then are not available for scaling. I think nobody knows really well, but I will have that feeling that maybe they're not available. So in a supernova, it's probably possible, and in neutron star maybe not. So that's my feeling.
Yeah, no, I agree with that. Like I don't think something heavy as that would like probably exist. You have what? Muons, yes.
But in the proto-neutron star, the temperature is in excess of the.
Right, but yeah, but the muons are also related to just having that the electron's chemical potential is larger than the muon mass, right? Yeah.
Any more question or comments? So I would like to thank again both speakers. Thank you, really, thank you very much.